Alrighty, for the viewer at home, what you should do right now is watch the high mass stars video that is linked as the first slide in the high mass stars Google Slides presentation, because we are now moving on to the high mass stars chapter of the book, which I think is chapter 15, as a matter of fact. So, onwards and upwards. So, remember that with a low mass star, it climbs up the giant branch after leaving the main sequence. High mass stars wander back and forth across the top of the HR diagram instead. So high mass stars move horizontally back and forth across the HR diagram after leaving the main sequence. So in other words, when they evolve off the main sequence, they pretty much do so at constant luminosity, it turns out. And there is a region in the HR diagram, which we'll get to later, called the instability strip, where when a high mass star that has moved off the main sequence is in the instability strip, it becomes a pulsating variable star. And in fact, that's key to our being able to know how big the universe is, because the Cepheids are high mass evolved stars that are in this instability strip. Cepheids have a period luminosity relation. We know the period of the pulsations from the light curve, from its brightening and dimming and brightening and dimming, we can figure out how luminous it is, and because they're bright enough to see in external galaxies, we are able to tell that external galaxies are in fact other galaxies. That's how Hubble discovered that, and now that's well known, we can measure how far away those galaxies are. And so they're the first link in the chain of the intergalactic distance scale, as a matter of fact. Okay? So, let's look at the evolution of a massive main sequence star. It begins similarly to a low mass star. A massive main sequence star burns hydrogen in a convective core. Remember that the cores of high mass stars are convective and the envelopes are radiative, which is flipped around from low mass stars, where the core is radiative and the outer envelope is what is convective. So it's still true that what happens in the core, kind of stays in the core as far as the star's life, while that hydrogen in the radiative envelope isn't getting mixed down into the core, and so when the core runs out of hydrogen, there will still be fresh hydrogen to burn surrounding the core. And it's not degenerate when helium burning begins, so there's no helium flash. And then I say no because this illustration from one of the intro textbooks I've used in the past says, then immediately begins helium in its cores and leaves the main sequence. No, not as far as I know. I've never been given that impression before. So no, it first does the hydrogen shell burning thing, builds up enough helium in the core to have the core contract at 100 million Kelvin, and then helium burning begins, but gradually, both in high mass stars and in higher mass, low mass stars, so to speak. Helium burning in the core begins gradually. But unlike a low mass star, we get past helium burning. The sun will never go beyond helium burning. It will never fuse carbon in its core. That carbon core is going to be its final remnant, the white dwarf. But in a high mass star, the carbon core will become hot enough to fuse carbon, as the video said, into a number of different elements. And so in high mass stars, we get a whole sequence of stages of elements fusing in the core. And each sequence begins with core fusion, and the core runs out and it switches to a shell surrounding the core. So we get a whole series of nuclear burnings. So the ash of one reaction becomes the fuel for the next as the star evolves a layered structure. Now, this is not to scale. It's always true that all this is happening in a tiny region, not much bigger than Earth in the center of the star. So tiny that you couldn't show it clearly on this scale. So they've greatly exaggerated the size of the core compared to the rest of the star here. So, eventually, we evolved this onion-like structure, they always like to say, although an onion isn't really spherical like this. But if you cut through an onion perpendicular to the axis that has the root coming out one end, you see what looks like rings, right? And so this is kind of like that, only it's a spherical version of that. So you got your non-burning envelope, and then as you move in towards the core, there's a hydrogen burning shell, a helium burning shell, a carbon burning shell, a neon burning shell, an oxygen burning shell, and then a silicon burning shell that is, among other products, producing iron in the core. So they say here at the end, the degenerate iron core sits within onion-like, quote-unquote, shells of progressive nuclear burning, as in a low-mass red giant, burning occurs in a tiny dense region at the center of the giant bloated star. So in other words, this whole region here is only about 0.01 solar radii across, which is comparable in size to the Earth. Yeah, the Earth's about 100th of the sun's radius in radius. So it's 0.01 solar radii in radius, so about twice that in diameter. Whereas the star itself can be like 1,000 times the sun's radius. So a tiny little region in the center is where all the action is happening. And the thing is that iron is special because, in particular, iron 56 is the nucleus which has the lowest mass per particle. Or in other words, it has the highest binding energy per particle, which means that if you fuse anything with iron 56, the products have more mass than the reactants do. If you fuse anything with iron 56, you make something which has more mass than the iron nucleus plus the thing that you fused with the iron nucleus. So unlike when you fuse hydrogen into helium, where a helium nucleus has less mass than the 4 protons that fuse to make it, or if you fuse helium into carbon, where carbon-12 has less mass than 3 helium nuclei does, and so forth. In all of those cases, you are converting mass into energy with each nuclear reaction. Iron 56, if you try to fuse iron, you have to turn energy into mass in order to do that. In other words, it is an endothermic reaction instead of an exothermic reaction. It requires energy instead of releasing energy, which means that iron cannot serve as a nuclear fuel for the star. And that's why the star is doomed once it builds up an iron core, because that's it. It's not going to be able to undergo iron fusion in order to keep desperately, if you will, not that the star is really like, oh my God, what am I going to do? Right? So we're anthropomorphizing when we say things like, the star is trying to continue to support itself against gravity. No, it's just obeying the laws of physics. It has no personal stake in this. It doesn't know anything about this. But the star has run out of options. It's got no more fuels available in order to keep things going once it builds up the iron core. So this is illustrating this idea. There's the mass per nuclear particle versus the atomic mass. And the bottom of the curve is at iron. So fission releases energy above that. The reason why nuclear power plants can fission uranium to get energy is because the products have less mass than the reactants. When you're above iron 56, fission produces lower mass products than the nucleus that fissioned in order to form them. Below that, then in general, fusion produces energy because you can produce something with a lower mass. So iron 56 is the border between the two. So when iron builds up in the core, the star is doomed, and that's ultimately what's going to make it blow up good. Yes?
On the slide before, is the layers, are they in the convective part, or are they just really deep into
You know, so the convective part is when it's on the main sequence doing the CNO cycle thing. I don't think it's convective, and that's a great question. I don't think it's convective anymore at this point because that would screw everything up, right? So I don't believe it's still convective when it's undergoing all of these fusions. Yeah, that was referring to the CNO cycle when it was on the main sequence. Yeah. All right, so our star is going to blow up good. He went through describing the lifetimes of various fusions. It's going to depend on the mass of the star. Here's for a 25 solar mass star, and what it comes down to is that every fusion stage is faster and faster, right? So for this 25 solar mass star, Hydrogen burning in the core on the main sequence is only 7 million years, long by human standards, but very short from star standards, right? That's less than 1,000th of the sun's lifetime. And helium burning is 700,000 years, so 1/10 as long. Carbon burning in the core only 600 years, neon burning a year, oxygen burning 6 months, silicon burning 1 day. 1 day. So, you know, we were used to thinking of stars kind of taking their time, even the highest mass stars, millions of years before anything happens. But when you get to the end, things are progressing very rapidly. The silicon burning is only going to last around a day or so. And you can't tell from the outside that it's reached that stage. So when we look at Betelgeuse, we can't tell if it's still burning helium in its core versus if it's burning carbon in its core. We don't know where it is because you can't tell from the outside because they just wander back and forth along the upper part of the HR diagram, and they retrace their path pretty much. In other words, multiple interior stages could correspond to a given location on the HR diagram for one of these high mass stars. So for all we know, when we see Betelgeuse tonight, it might be burning silicon and it's going to blow up good really, really soon, or maybe it's still millions of years away from blowing up. We just can't tell. So you just got the excitement of waiting. Blow up, come on, blow up! Right? Hasn't come through for me yet, but I've always got my hope going. I'll miss it, but I want to see it. Meanwhile, we're going to talk about the collapse of the iron core when it can no longer support itself. It takes like a quarter of a second. There's what we call core bounce, because it will stiffen up when neutron degeneracy pressure kicks in and then bounce back again, milliseconds, and then boom! The supernova, it says 10 seconds, it takes a few hours for the shock wave to make its way out to the surface. So you don't see the star immediately do anything when the interior has initiated the supernova detonation, but it's only a matter of time. It's only a few hours for the shock wave to get out to the surface of the star, and then it would just be spectacular. Okay? So, let's talk about the end stages when you've got the iron core and it's doomed. So it's support again. When we talk about white dwarfs and neutron stars, we'll say in detail how degeneracy pressure works. But for now, remember it's a quantum mechanical phenomenon due to the Pauli exclusion principle, forcing the electrons in the core to much higher energies than they would have from classical thermal physics. The silicon burning shell keeps dumping iron on the core, and there's a maximum mass, about 1.4 solar masses, that degeneracy pressure can support. And so eventually, the core becomes too massive for even very stiff electron degeneracy pressure to support it, and that's what's going to make the star blow up. So not even electron degeneracy pressure can stop the collapse of an iron ash core. And so it begins to collapse. As the core collapses, the core temperature climbs so high that thermal gamma rays photodisintegrate the iron. In other words, the temperature is so high that the gamma rays from the blackbody radiation have enough energy to break apart the iron nuclei. So the star has spent its entire lifetime building up iron in its core, and then in a flash, it photodisintegrates it. So it just breaks the iron nuclei apart into mostly just helium nuclei and alpha particles. Alpha particles are very stable, so they tend to be the fragments that are being produced by this. And the core becomes so dense that electrons are absorbed by protons in atomic nuclei, forming neutrons and releasing energetic neutrinos. So this is what we call neutronization. So protons can combine with electrons to form neutrons and neutrinos. So this is how you make the neutrons that are going to become the neutron star when you're making a neutron star. And then meanwhile, neutrinos are produced as well in that reaction, and the neutrinos actually carry away more energy than anything else in the explosion. And in fact, in 1987, we saw a burst of neutrinos from the supernova that blew up that year in the Large Magellanic Cloud before we saw anything else. And then, so neutrino detectors detected an extra flux of neutrinos. I think it was like 6 of them, something like that in one of the, not a huge number, but way beyond, it would be a large statistical fluctuation, too large to be just a coincidence. And then sure enough, they saw the star blow up shortly thereafter. So it's one of those things that's like, I guess our models of supernova explosions have something to them that they would predict that you get a bunch of neutrinos streaming out as the core underwent neutronization. And so then photodisintegration and electron absorption robbed the core of pressure support because it's the electron's degeneracy that was holding the core up. So the core collapses even faster, but once it becomes dense enough, once it gets down to when it gets up to about the density of a nucleus, once it gets to about the size of a neutron star, 10 kilometers or so in radius, the nuclear forces suddenly become repulsive and the overcompressed core bounces. So that means that the surface springs back again and meets material that's crashing down on it at about 1/4 the speed of light from above, and that sets up a shock wave, essentially. So driving its outer layers outward through the stars, and so notice I'm kind of repeating there, this is from one big figure. The expanding shock is strengthened by the pressure of a hot bubble of trapped neutrinos from the core. Back in the 80s, computer models had trouble getting supernovae models to explode, as in, this is saying it's time to temporarily interrupt our program to see how SpaceX is doing. So we temporarily interrupt this program.
See how long it's going.
Yeah.
Out into the solar system
All right.
to orbit around the sun.
Let's do it.
So that gives you a feel for the sequence of events we're planning on today's flight. So now, at T minus 4 minutes 45 seconds and counting,
Alrighty.
let's witness the test